Okay.
Okay, welcome everybody to the HAO colloquium today by Hang Yang Liu. Hang Yang is a PhD student at the Department of Arts Sciences, University of Hong Kong. His research interests lie primarily in theoretical and computational space plasma physics. He is visiting HAO as a NCAR fellow and will be working with Dr. Yu Hong Fan on implementing new high-order numerical schemes to the magnetic flux eruption MXE code for MSD simulations of coronal mass ejection initiation. Today, he will be speaking on gas kinematic schemes for solving the magnetohydrodynamic equations with pressure anisotropy.
Yeah, thank you. So I'll be talking about a new scheme that we have developed recently, which is called the gas kinetic scheme for solving the magnetohydrodynamic equation with the pressure anisotropy. So quick outline. First, I will be talking about anisotropic plasma and also some of the energy applications. And then I will be talking about why we start this research and the method. So, and then I will show some test results. So here's an example showing the observed. Okay, so what is anisotropy and why important? So anisotropic plasma refers to situations where the plasma exhibits anisotropy velocity distribution functions and the temperature. And in situ and remote sensing measurements show that the magnetized crystallized or weakly conditioned plasma is anisotropic. So here is an example showing the observed anisotropy in the solar wind. The plot shows the anisotropy of the total distribution function of the slow, intermediate, and fast solar wind at increasing distance from the sun. So the dashed line here, oblique dashed line, is in the middle of each plot, small plot. Okay.
And it's a pointer. This pointer.
It's a pointer. Okay.
Yeah.
I think okay. So this one is the magnetic field in each plot. So, so the bottom three pictures describe the total distribution function of the solar wind 0.3 AU away from the sun. And the middle three pictures shows the distribution function around 0.5 AU away from the sun. And the top three pictures shows the distribution function around 1 AU away from the sun. So we can see there's a high degree of anisotropy in the solar wind at the beginning, and it gradually decreases as the distance from the sun increases. So here's another example. Plot here is a histogram referring to dark solar wind at 3 different distances from the sun. So from the plots, we can see that the anisotropy distribution is constrained by the instabilities. The solid lines shows the solid lines here shows the threshold of ion cyclotron instability. Ion cyclotron instability happens when the perpendicular pressure is much larger than the parallel pressure. So we can see it's larger than 1 because of the perpendicular pressure is larger than the parallel pressure. The dot lines show the threshold of mirror instability, which is similar to the ion cyclotron instability that happens when the perpendicular pressure is much larger than the parallel pressure. And the dashed line here shows the mirror, the threshold of fire hose instability. And fire hose instability happens when the parallel pressure is much larger than the perpendicular pressure. And anisotropy can be also important in the planetary system. So here's a plot showing the plasma observed near the local node in the Jupiter's magnetosphere with a Galileo spacecraft. So the plot here shows the density and the temperature for the heavy ions with the mass charge ratio equal to 16, and for the hydrogen ions. So this is the top three are the plots for the heavy ions, and the bottom three are the plots for the hydrogen ions with mass charge ratio equal to 1 as measured in the local unit. So just by looking at the plot C and the plot F, we can see that the plasma is different from isotropic system very much. Okay, so what is MHD and why important? There are mainly three types of three ways of modeling astrophysical and space plasma. The most expensive way is for sure the kinetic and particle way. This kind of method can track individual particles or just use distribution function to describe the system. So this method gives you electron scale physics, but they're very expensive. The MHD method treats plasma as conducting fluid. So basically it solves the mass momentum energy equation, as well as the Maxwell equations. This method has low computational cost and gives very good description of the system most of the time. The hybrid method is something in between. So it solves the ions with a kinetic or particle method and solve the electron with a fluid method. So this gives you ion scale physics, but still costs a lot. The hybrid and the particle method are quite nice, but they are too expensive to be applied to the global simulation. So it becomes an advantage to use MHD to describe a very large system. So here are some examples of MHD simulation applications. The first example is the MFE code. The movie here shows the erupting magnetic flux flow in one CME event. There's another example. Here's a simulation of small-scale dynamo by using the program code. And the MHD simulation is very powerful, not only in the solar physics, but also in the geospace and the planetary science. For example, the left figure shows the Earth magnetosphere simulation by the famous LFN code 40 years ago. And the right figure shows the Jupiter's magnetosphere simulation by using the Chimera code, which is the successor of the LFN code. However, most MHD solver only solve ideal MHD with isotropic pressure. So one of the reasons is that solving an isotropic MHD equation numerically is quite challenging. So one example code with the ability to solve the anisotropic MHD is the beta Earth code by Michigan Group. The figure here presents the Earth's magnetosphere and two TH satellites and across the baseline magnetosheets and bow chart. And we can see the plasma anisotropy behaves differently in a different region. And another example is the alpha wave solar wind model, also called the OSEM model, with anisotropic pressure also by the Michigan Group. The plot here shows the simulated proton pressure and anisotropic ratio. So the P perpendicular to the P parallel and the solar wind speed in the y equal to 0 and the z equal to 0 planes for a Carrington rotation event. So motivation. Fluid description of plasma is widely used in diffusion, phase, and astrophysics. The underlying assumption is that the distribution function is isotropic. However, in the weakly or non-crystalline plasma, pressure is usually anisotropic. Parallel and perpendicular pressures with respect to the ambient magnetic field are needed in the pressure tensor. So the bit head here is the unit vector of the magnetic field. And there are some examples of anisotropic fluids and astrophysical plasma system. For example, the galaxy cluster plasmas, the solar wind, and also in planetary magnetospheres. So we want to develop robust and accurate numerical scheme to solve anisotropic energy equations. So isotropic versus anisotropic energy equations. The basic idea of both sets of equations are the same. They both solve the mass, momentum, energy equation as well as the Maxwell equations. The main difference is that the pressure term in the ideal MHD is just a scalar P times the identity matrix, while in the anisotropic MHD, the pressure tensor needs to account for the pressure difference between two components as well as the magnetic field direction. Also, we can see the anisotropic system requires two additional entropy equations for solving the pressures. We start from the double adiabatic MHD, also called the CGL MHD equations. So through Boulder and Rowe originate the CGL or the double adiabatic equations, assuming an isotropic distribution. Then integrate the moment of Russell equations to get equations for the perpendicular and the parallel pressures. Perpendicular pressure equation is usually linked to the first adiabatic invariance, which is also called mu, the magnetic moment. And the parallel pressure equations is related to the second adiabatic, representing that in the flux tube, the time variation is low relative to the bound time. And later, HAO showed that double adiabatic or the CGL theory can be written in the conservative form. And then it also showed that the CGL equations can be viewed as having a perpendicular gamma equal to 2, corresponding to having a degree of freedom 2. And the parallel gamma equal to 3, corresponding to a degree of freedom equal to 1. Such system can be generalized to a more generalized form as the double polytropic system, in which the gamma values can be more flexible and depends on the problems. So solving for a non-conservative form is challenging, especially when dealing with discontinuities. And the conservative forms is more straightforward to solve using the gap schematics plus functions. Energy conservation is also checked by solving the plasma or total energy equation together with pressure equations. So we choose to solve this set of equations. We solve the mass equation, momentum equation, and the Maxwell equation. Also solve the perpendicular pressure equation and the plasma energy equation to get the average pressure. And then the parallel pressure is calculated by using the average pressure and the perpendicular pressure. We can also solve the equation on the other way. So we derive the equation to solve the parallel pressure, and it can provide a good check. The pressure anisotropy cannot go without bound, because the high frequency waves and the micro instabilities feed on the free energy in the pressure anisotropy and act to isotropize the pressure, limiting the pressure anisotropy. So there are many three types of instabilities we're considering. When the parallel pressure is too large, five-fold instability can happen. And when the perpendicular pressure is too large, pure instability and the ion side electron instability can happen. We use a relaxation method when any instability is triggered, and so the pressure anisotropy is reduced in the given time tau. Then also the tau can depend on the growth rate of the instabilities, or we can just use a constant The basic idea of gas kinetic schemes for plasmas is to consider the fluid on each side of a cell as a microscopic distributions of non-interacting particles. So the plot here shows the left and right states at the interface and the corresponding flux. And the macroscopic tensor variables are derived from partial movement integrals on both sides of the interface. So we use the mass equation as an example here. The right-hand side of the equation consists of two parts, which are the flux left and flux right in the figure. So the flux left represents the particle going from the left to the right. So the particles are hitting the left interface, and we integrate the zeroth movement integral of the left state distribution function from 0 to infinity. Flux right represent the particles going from the right to the left. So the particles are hitting the right interface, and we integrate the zeroth movement integral of the right state distribution function from 0 to negative infinity. And then after we calculated the flux, we update the macroscopic variables with the finite volume framework. For anisotropic plasmas, the gas kinetic scheme becomes more complex. Step one, we start with the common diameter distribution, where the A is the perpendicular thermal speed, and the B is the parallel thermal speed. In the ordinate coordinates, the calculation is very complicated, so we go to the step two with the coordinate transform. The step two is the most important part. We rotate the coordinate system so that the new xy plane contains the magnetic field. Now the z direction computation is separated, and we don't have any magnetic field in z direction. So the computation is pretty simplified, and we get a new distribution function in the new coordinate system. First step is to calculate the flux for the equation in the new coordinate. For example, the mass flux is the sum of two partial integral of the zeroth movement of the distribution function. And the momentum flux is just the sum of the first moment integral of the distribution. The first adiabatic invariant flux is then the sum of two partial integral of perpendicular product speed squared over 2b, where the b is the magnetic field. Okay, so we need to derive the exact equation to use in the code. And this is the calculation of the flux going from the left to the right. So it looks quite complicated, but it's actually not that computationally expensive. There's only one error function and one exponential function on each side of the flux. So it's the same as the gas kinetic scheme for ideal MHD. The flux threading the interfaces are the sum of the two partial integrals. So we need both flux left and flux right to get the actual flux. And when A equals B, which means the parallel pressure is equal to the perpendicular pressure, the flux function recovers the ideal energy scheme. Okay, so we want to show some test results. The test bed is based on the numerics of the LFN code. Essentially, the scheme is first order, so it can be quite diffusive. So we use high order reconstruction to get a more accurate left and right states, and use those left and right states to do the flux calculation. So here's a test problem we did with a numerical scheme. This is the two-dimensional smooth problem. Nonlinear unmaterial atom waves propagate at a specific angle, and in anisotropy MHD, the pressure anisotropy affects the propagation speed of the atom wave. So the alpha weight is not only determined by the magnetic field only, but pressure can also be important. Wave speed is larger when the perpendicular pressure is larger. The alpha weight becomes lower when parallel pressures become larger. We run the test with different perpendicular and parallel pressure values, while keeping the average pressure to be 0.5, and test different anisotropy pressure ratios. This is a set of geograms showing the magnetic field perpendicular to the wave vectors as a function of time and position. The x-axis is time, the y-axis is the position along the wave vector, and the color shows the magnitude of the perpendicular B field. So in the plot A, the pressure is isotropic. In the plot B and C, we have larger perpendicular pressure, and in plot D to the F, we have larger parallel pressure. So we can calculate the numerical speed by drawing the slope of the pattern as the yellow arrow. Then after we calculate the numerical speed, we compare that with the analytical speed, and we find that they agree very well. We also test a one-dimensional MHD structure problem and compare it with the result in another published JCP paper about anisotropy MHD. You can see the results agree well, and there are certain differences between ideal and anisotropic cases. For example, the contact disk continuity involves not only variation in the rho, but also in the By and the perpendicular and parallel pressure. The blue line here is the parallel pressure, and the red line here is the perpendicular pressure. So also we can see the selective enhancements of the parallel pressure across the slow shock. So this can be understood by just looking at the first and the second adiabatic invariance. Increasing density and the decreasing magnetic field naturally lead to enhancement of the parallel pressure. And here's a more complicated outside time problem. Basically, there's a collision of MHD shock interacting with themselves. The left figure is just the ideal MHD scheme. And in the right figure, we use the anisotropic scheme while enforce the perpendicular pressure equals to the parallel pressure at the end of each time step. So we can see the left and right are the same, showing that the new scheme exactly reduces the ideal MHD when two pressures are the same. And this is the outside time problem with the new anisotropy scheme without enforcing isotropy. To the left is the perpendicular pressure, and the right is the parallel pressure in the outside time problem. The initial state is isotropic, while the two pressure components evolve independently according to the double adiabatic theory. And we can see the new scheme can handle complicated shock interactions. We also performed the GEM magnetic reconduction challenge to see if the scheme can provide a good description of magnetic reconduction process. So first, to find that there's no fast reconnection, since we did not include any Hall physics that generally determines the fast reconnection rate. We also then realized there's a 5-hole size anisotropy, which means the parallel pressure is greater than the perpendicular pressure. This can be a straightforward outcome of the double adiabatic theory. When considering the magnetic reconduction, The reduction of magnetic field strength and the increase of the density across the plasma sheet boundary naturally leads to pressure anisotropy, with parallel pressure greater than the perpendicular pressure. Okay, quick summary. We developed a new anisotropy MVC algorithm. The flux of conserved variables across cell interface are calculated by integrating Boltzmann-like distribution function over velocity space. The numerical method is reliable and robust and can be extended to the more generalized thermopolytropic system. We perform one-dimensional and two-dimensional tests, and the results are good. We have provided an example Python code and also write a meta paper about it. And the future work will be adding more physics, for example, the Horton and the multi-fluid implementation. Also, we plan to apply the new scheme for planetary modeling, for example, Jupiter, and then possibly CME simulations. Okay. Finally, I want to say thank you to everyone here. And also thank you to the HAO and the NCAR program for providing me such a good opportunity to visit, learn, and share here. Thanks.
Questions? And also the online people, just unmute and ask your question. Just have a quick question about your reconnection simulation. This is one.
Yeah.
So what is the significant difference by putting it in this logic? What is the, in terms of reconnection rate compared to isotropic case?
So in the geospace environment modeling, also called the gem reconnection, the reconnection rate is not much difference, but there's some other papers that doing research about other type of reconnection rate, other type of reconnection using anisotropy scheme. Their results show that the anisotropy scheme gives you slightly faster, but it depends on what kind of reconnection you're studying. And especially in the reconnection rate, there's the anisotropy scheme the anisotropy system will change the configuration of social regions in every type of reconnection, but it depends on the problem of each type of reconnection. So reconnection rate and social region will have some changes. It depends on the problem.
Other questions?
How much more expensive is it computationally compared to the isotropic scheme if you just estimate the floating point overhead dealing with the anisotropic scheme?
So I only compare the anisotropy scheme in the gas kinetic and the isotropic scheme in the gas kinetic, because in the Gamarian and LFN code we use gas kinetic scheme for the flux function. It turns out to be not that much more expensive, around 20% at most in partition, I think.
And are there additional time step constraints coming from the anisotropic treatment?
Yes, because fast mode speed and the alpha wave speed got changed in the new system. So somehow you need to consider the fast mode, the sound speed in the perpendicular and the parallel pressure in the parallel direction. So usually we need to, if the simplest way is just to turn the CFL number smaller if you use the old DT scheme. Otherwise, you need to change your DT functions to the new system according to the new characteristic with speed. but it won't be changing a lot.
Okay.
Most constraining is the fastball speed. Still the most constrained. Determining this.
Yes, due to fastball speed. But the fastball speed is changing. It's different. The speed in the fastball speed is different in the new system and the attenuation system.
Hi, it's Mike Wilperter online. I'm just curious for the Orszag Tang ones where you've got the strong shocks going on. What kind of limiters are you applying to the fluxes after you do the flux calculation for the left and right state?
Sorry, what?
Are you applying any numerical limiters to the left and the right state to keep the solution TBD for these instances where you
we use numerics of LFN code, so we use order reconstruction and the TDN limiter. And the initial state here is just isotropic. But they evolve independently.
Got it. Thank you.
Yes. Hello, Hong Yang. This is Philip George. I'm just currently in Switzerland, but I enjoyed the presentation. I think it's a very important step to take. And I think going between the fluid and the kinetic physics is really going to reveal a lot of interesting things, in particular for the problem of coronal heating as well. So congratulations on a nice piece of work. I had a question, though, on when you assume two Gaussian or two Maxwellian distributions, one parallel to the field and one perpendicular, is there any real justification in physics for that aside from it's very convenient and it captures some of the observations that we see in plasmas?
Yeah, so the reason why we are using the Maxwellian is the most common one and it's simpler. And definitely we can use other distribution, for example, bicapa and others. But the main step is the first step 2. We need with any other distribution function, we still need to use a transformation in the step 2 in order to simplify the calculation. And other steps will follow the similar steps. So you can use any other distribution function as long as it's appropriate.
Okay, and I'm particularly interested in the sun as opposed to geospace, but and that's an area where things like transport are very important. So it's not just the anisotropy of the distribution functions; it's also the kind of skewness. So that if you have a small imbalance between the upward and downward flux sides in the distribution function, then you get a lot more transport. And so, for me, I always worry about classical transport coefficients as applied to the corona, where the mean free path might be a significant fraction of the structure that you're looking at. And so basically, I'm just wondering, aside from the work you've done, if there's reasons to think about perhaps introducing anisotropies into these distribution functions, which are velocity anisotropies, not just angular ones.
The question is a little bit too long for me. So
yeah. Well, if you have things like the classical derivation of things like heat conduction relies on there being a small difference between the upward flux of electron heat versus the downward, and I worry a bit about those classical coefficients in the sun's corona, given the mean free paths that can be very long. So I was just wondering if in splitting up the distribution function into two, a parallel and a perpendicular plane,
okay.
then if you also could do something with parameterizing an asymmetry in the velocity distribution function to look at some things in transport coefficients. I know this is a very different.
Now I understand what you're saying. Yes, what you're saying is definitely right. So yeah, we can modify the distribution function.
Yeah.
And also, this is for other terms. This is the problem of closure and something. So we can also add other terms in terms of the problems we are considering. Yeah, for sure. We can also modify the distribution function to make it more realistic. Yeah.
Okay, because one of the empirical things I've learned from observing the sun is that, I'm really starting to wonder whether one can use these classical diffusion coefficients or not. And it depends of course, what the source of the high energy particles is and what the asymmetry is. And so it's really a Boltzmann problem as opposed to a kinetic fluid problem. But, I think there is a possibility for solar physics to look into the kind of approach you're using, but perhaps looking at, this kind of velocity anisotropy in terms of not just angular. Yeah. Okay.
Yes.
Thank you so much.
Thank you. Thank you. Yeah.
Other questions? One from online.
How is the Basferos code? So you said they implement the Awesome code, you implement the pressure anisotropy, but they're not using the gas kinetic scheme.
No, they are using Rusanov and HAL most of the time.
So the flux function is just like
So we are solving basically the same set of equations, but they are using different flux function.
instead of this using the distribution function
Yeah.
to get the gas.
So applying something like this to the corona, in particular, if you have a very complicated regime, you have kind of the more quiescent corona, and then you might have solar flares where really crazy things happen. And likely the anisotropies and even the shape of the distribution functions you expect in these different regions might be quite different. So is there in principle a way in your scheme to generalize the code that you even can have different distribution functions in different regions of your domain depending on the physical conditions?
Yes, I think so. But yeah, you can definitely modify the distribution function, but then the moment integral you derive need to recover the fluid distribution because the basic principle of the gas kinetic is after you integrate the moment, you recover the fluid equations.
Mhm.
Yeah. Yeah, I think it's doable to use different distribution in different regions.
You have to pre-calculate.
Yeah, we need to pre-calculate
Yeah.
those equations. Yeah. Right. The basic method should be the same as using by Maxwell.
Have you implemented it in numerical? And that's probably in full numerical.
In the future.
Question? Let's thank our speaker for a very nice talk.
Thank you, Hong Yang.
Thank you.